Hello, this is Mr. White, and this video is on related rates, part 3. Here are the two exercises we'll cover in this video. Let's proceed. We have a hot air balloon rising vertically, and it's being tracked by an observer 4 kilometers away from the liftoff point. At a certain point in time, the angle between the observer's line of sight and the horizontal is pi over 5. And that angle is changing at 0.2 radian per minute. How fast is the balloon rising at this moment? So step number 1 in our 4-step process has us identifying the given quantities and quantities to be determined and making a sketch. And we definitely need to draw a sketch for this one. So step number 1, let's consider this hot air balloon rising vertically. So here's the ground and here's our hot air balloon rising vertically, and there's an observer 4 kilometers away, and the observer is tracking this balloon. So there's the observer's line of sight, and again, the observer is 4 kilometers away, so let me document that. And notice that that 4 kilometers is not going to change. There's nothing that suggests that that observer is going to get any closer or further away, at least in the horizontal direction, from the balloon. So we'll go ahead and put 4 kilometers. In contrast though, when the problem states that that angle is pi over 5, the angle between the line of sight and a horizontal, we are not going to label that pi over 5 because that is a variable quantity. We are going to simply call that theta. Again, a moment later the balloon's going to be higher and the line of sight will have changed, and that will no longer be pi over 5. So again, make sure that for quantities that vary, give them variables. Likewise, what about this distance? Are we going to put an actual number or are we going to put a variable? Well, the balloon's rising, so it is varying. We'll call that h. Let me comment real quickly. You may recall from pre-calc that there are times when we'd measure items and we would draw this horizontal line and then we'd consider the eyeball height of the observer. We're not going to bother with that this time. We're going to justify that because we're dealing with 4 kilometers here, and this drawing is clearly not to scale. But if we're dealing with 4 kilometers horizontally, that eyeball height is going to be so insignificant that we're just going to ignore it. Okay, so what do we need to write off to the side here? Let's see. We've got some of the information documented in the picture. We need to state that at the time that we're interested in, theta will be pi over 5. So here's where we capture that information, not on the picture. And we also capture that theta is changing at a rate of 0.2 radian per minute. So d theta, change in theta with an infinitesimal change in time, is going to be 0.2 radian per minute. And as far as units go, again, radians are an optional. It's optional as to whether you write them down. So I just put theta as pi over 5. I could write radian up here, but I didn't really have to. But I'll go ahead and leave it there. And what is it that we're trying to find? Well, we want to find how fast. That's our hint that we're dealing with a rate, or we're being asked for a rate. How fast is the balloon rising at this moment? So what's the change in h with respect to time? That's what we want to find. Okay, so that was step 1. Step 2, write an equation. Write an equation involving the variables whose rates of change either are given or are to be determined. So here's the rate that was given. Here's the rate that's to be determined. So step 2 says we need to find an equation that relates theta and h. So this is where our picture really helps out. We can look at that picture and look at the right triangle that we have. And again, the fact that we're neglecting eyeball height means that we're just picturing a right triangle in here. We're not worrying about the eyeball height. And how does theta relate to h? Well, pretty clear that trigonometry is coming into play, right? So which trig function is going to relate those? Given where theta is located, we are looking at a quantity that we know that is adjacent to theta, and the quantity that we want to know or that we're interested in is opposite. So opposite and adjacent, we're dealing with tangent. So let's say that tangent of theta equals h over 4. And I'm going to try to be a little more careful with units. I have to admit, sometimes I'm a little bit guilty of being sloppy with writing the units when, in the related rates. But tangent of theta is h, and h will presumably be given in kilometers as well, over 4 kilometers. That's step 2. We've related theta and h. So, step 3. Using the chain rule, implicitly differentiate both sides of the equation with respect to time t. All right, step 3, let's copy this on down here. And in step 3, we do d over dt of both the left and the right-hand side of the equation. And when we derive tangent, we get secant squared theta. And since theta and t are 2 different variables, we write times d theta over dt equals, think of this right side as 1/4 h. And so if you derive 1/4 h, you will get just 1/4. And again, due to the different variables, times dh over dt. And I guess I really should put 1 over 4 kilometers. Almost got caught being sloppy with the units again. So finally, step number 4, substitute in all those values that we documented back in step 1 and solve for the required rate of change. All right, so way back at step 1, we had said that theta would be equal to pi over 5. So we'll write secant squared of pi over 5. And then d theta over dt we said was 0.2 radian per minute back in step 1. And that equals 1 over 4 kilometers times dh over dt. Okay, let's rearrange that algebraically. I'm going to switch sides here so that I can get the dh over dt on the left side. And let's multiply that 4 kilometers, which is in the denominator there. Let's multiply it over to the other side and get 4 kilometers. It is being multiplied by, let's multiply it by this next, times the 0.2 radian per minute. And rather than multiply by secant squared of pi over 5, since we're going to be putting that into our calculator and our calculator doesn't have secant, let's remind ourselves that multiplying by secant squared is the same as dividing by cosine squared. So just in anticipation of using the calculator, I'll write cosine squared of pi over 5 here. And when we type that into the calculator, I've just done that ahead of time for time's sake. I see that 4 times 0.2 divided by cosine of pi over 5 squared, and notice how I typed that in here, is going to give us about 1.222. So we'll say 1.222. And when we look at the units, remember how I said radian was optional? It's because in situations like this, you basically just ignore the radians, and you see that we get kilometers per minute. Okay, so that's 1.222 kilometers per minute. We have determined how fast that balloon is rising. All right, fun stuff. Let's go on to the next one. We have a police car 20 kilometers due north of New Orleans at time t equals 0. That's when you start the stopwatch. Police car is traveling southbound at 160 kilometers per hour. We're using metric. We're honoring New Orleans' European heritage here, apparently. Your getaway truck, what have you done? Your getaway truck is already 30 kilometers due east of New Orleans, traveling eastbound at 140 kilometers per hour. We're assuming that both vehicles keep a constant speed and direction. So given that, calculate the rate at which the distance between them is changing at time t equals 0 and 5 minutes later. A lot of times students don't completely understand what's being asked, but I think once we draw a picture, we'll get a sense of what's being asked. So let's get into step 1, which of course is identifying given quantities, quantities to be determined, and making a sketch. So here's New Orleans. And a police car is 20 kilometers north of New Orleans. So put cop. And 20 kilometers north, and traveling southbound at 160 kilometers per hour. So again, it's tempting to want to label this distance as being 20 kilometers. But remember, the cop is moving. That 20 kilometers is not static. It is not constant. So let's call that distance, let's give it a variable. Let's call it y, how about? So that's y, and off to the side we'll say, okay, the time we're interested in, when t equals 0, y is 20 kilometers at that time. How do we reflect that the cop is traveling southbound at 160 kilometers per hour? Well, that's what the change in y is, right? So we'll put dy over dt equals 160 kilometers per hour. Now, I do have something that's a little bit incorrect there. Do you see what it is? It's very subtle, but it's one of those things we better be aware of. Notice that if the cop is traveling southbound, y is decreasing, right? So if y is getting smaller, that means that dy over dt is negative 160 kilometers per hour. Be careful of that. All right, at the same time, your getaway car is 30 kilometers due east of New Orleans. So again, we're not going to put 30 kilometers. We're going to call that x, because that is a variable quantity. It is changing. And off to the side, we'll put x equals 30 kilometers at a certain point in time that we're interested in. And dx over dt is going to equal 140 kilometers per hour. Now, is that positive or negative? We are headed away from New Orleans. We are going east in that direction, so x is getting bigger, so dx over dt is indeed positive. Okay, and what is it we're trying to find? We want to find the rate at which the distance between the two vehicles is changing. So we are interested in this distance right here. I would ask you to consider right off the top of your head, as the cop is going south, as you are going east, is that distance, is that hypotenuse there getting longer or shorter? Personally, I don't think it's totally obvious. So don't feel bad if you're not sure whether that distance is getting longer or shorter, but keep in mind that that's going to determine the sign of our answer. Let's call that length s, and the thing that we're looking for is how fast that quantity s is changing. So again, if it turns out that in a moment's time, when you're here and the cop is here, and if this new distance for s is longer than the previous distance, then ds over dt will be positive. If that new distance is shorter, then we'll find that ds over dt is negative because s is decreasing. All right, that was step one. Step two is where we write an equation that relates two quantities. Do you remember how we determine which quantities we need to relate? Well, you look at the rates that are involved in step one. This is one rate, here's another rate. We need an equation, oh, and here's a third one. We have three this time. We have three rates that we're dealing with. And we need an equation that relates them. S, x, and y. Well, I think it's pretty evident, don't you, which equation we're going to need? This is interesting because in the last exercise we had a right triangle as well, but in that last exercise we were interested in an angle theta. We're not really interested in any of these angles here. So we're not using trig, we're going to use our good old Pythagorean theorem. So step two, let's write x squared plus y squared equals s squared. Okay, step three was using the chain rule, implicitly differentiate both sides with respect to t. So step three is where we copy this equation down and then differentiate both sides with respect to t. And we proceed to say that if I differentiate x squared, I'm going to get 2x, and do the difference in variables times dx over dt. That's the chain rule. Differentiate y squared. Similarly, we'll get 2y dy over dt. And similarly, s squared will give us 2s ds over dt. All right. Step 4 is where we plug everything in and solve for the quantity that we're interested in. I'm going to do one thing. I'm going to make a choice here. I'm going to go ahead and solve for that quantity we're interested in, which was ds over dt. I'm going to go ahead and solve for that before we plug anything in. And that's just a choice that you're allowed to make. I'm going to start by saying if I divide both sides of the equation by 2, I'll divide out that 2. And then I'll get ds over dt equals what used to be the entire left side, without those 2's, of course. So I'll get x times dx over dt plus y times dy over dt. And then I'll divide that s over that used to be multiplied by the ds over dt. I'll divide that over and put it over s. Notice that if you wanted to get this completely in terms of x and y, instead of putting s, you could put square root of x squared plus y squared if you felt some need to do that. Again, that's a choice. Doesn't really matter. I'll just leave it as s. And let's recall our initial geometry. If I scroll back up to our picture, remember how we said that y was going to be 20 kilometers over here, right? And the x was going to be 30 kilometers here. So let's just recreate that geometry real quickly down here. Okay, there we go. Let's go ahead and find out what the hypotenuse is using the Pythagorean theorem. Okay, I just threw it on the screen. For time's sake, I'm going to trust that that was something you could do quite easily. And at this point, let's plug everything in. ds over dt equals that right there. Again, I'm going through this pretty quickly since this is just arithmetic and algebra. Remember, this is where something we documented here in step 1, the rates at which the vehicles are traveling. And if I simplify all that, I get this quantity. Notice that in the units, kilometers, kilometers, and I will end up with kilometers per hour. And finally, if I type that into a calculator, I will find that ds over dt is approximately 27.735 kilometers per hour. And that's telling us that the distance between the two cars is increasing with time, at least at that moment. Now, pause the video, take a breather if you need to. That may have been a little bit intense. But let's remind ourselves that we have one more part of the problem to do. We have to ask ourselves, how is ds over dt changing 5 minutes later? Well, the good news is that a lot of the hard work has already been done. So we're going to build off what we've already done. And let's go ahead and tackle that if you're ready. All right, 5 minutes later, let's think of what's happening. I'm going to recreate that picture again. So we got New Orleans down here. And up here is where the cop car is, and then over here is where you are. And let's remind ourselves how we started. I'm just going to summarize some of the information that we documented earlier. Originally, this distance was 20. This is 20, and I didn't want to write it on the diagram at the time, but I will now, just see where I'm going with this. That was 20 kilometers, and this distance over here was 30 kilometers. And we want to know what's going on 5 minutes later. This was at time t equals 0. We want to know what's going on 5 minutes later. Well, keep in mind that this cop car was traveling southbound at 160 kilometers per hour. And remember, that resulted in a negative 160 dx over, or dy over dt value. So negative 160 kilometers per hour times however many hours the car has been traveling. Let me move this over just a little bit more. And we are interested in 5 minutes later. So we've got some mixed units here. We've got kilometers per hour, and then we're given some piece of information in 5 minutes. So we need to resolve that. Let's change that 5 minutes later. Let's say that 5 minutes is 1/12 of an hour. And we'll say that because it is true. And now our units agree with each other, and I can put that 1/12 here. And notice that the hour needs to be treated as if it's in the numerator. And when you do that, notice that the hours go away, and that means that we've got 160 over 12 That's the distance that the cop has traveled in 1/12 of an hour. So the new distance will be 20 minus 160 over 12 kilometers, and that's going to equal 20 kilometers. So that's going to be my the new value for y that we'll plug in a moment here. We'll no longer be at 20 kilometers because after 5 minutes, the new y value will be 20 over 3 kilometers. And in fact, let me put y equals 20 over 3 kilometers. If we do a similar thing for this other value here, 30 kilometers, and you are allegedly traveling at 140 kilometers per hour, so we'll put plus. Now this was getting bigger, right? Your distance was getting greater from New Orleans, so we'll put plus 140 kilometers per hour times the same 1/12 hour. And once again, units work out nicely, hours go away, and we've got common units of kilometers. And here we end up with 125 over 3 kilometers, and that's going to be our new x value for u. If we were to perform Pythagorean theorem on that, a squared plus b squared equals c squared, right, using these two new values, we would get this hypotenuse that I just displayed on the screen. And again, I'm going through this quickly because this is just arithmetic that I know you can handle. So what do we do with all this information at this point? We go back up to that equation that we got earlier, right here at the beginning of step number 4, and we're going to plug it in again. Here are the previous values we had used. We're just going to plug in those new values into this same equation. So let's bring this down here. And plug in those new values. Okay, x will be 125 over 3. I'm going to go ahead and just, all the units are agreeing with each other, so I'm going to just forego the units for now until the end. So 125 over 3, dx over dt is still 140. And then y, our new y value is, let's see, 20 over 3. And dy over dt, we said was negative 160 kilometers per hour. And that was all over s, which is this crazy 5 square root of 641 over 3 kilometers. Okay, just to be consistent, I said I wasn't going to write the units. All this numerator is going to give us 14300 over 3. And so if I have 14300 over 3, over this denominator, the 3's cancel out. If I do 14300 divided by that 5, I would get 2860 over the square root of 641. And let me put the units back in there. I knew they were going to come out to be kilometers per hour. And that is approximately equal to 112.963 kilometers per hour. So that distance between the cop car and us is still getting bigger. Whoops, ds over dt. And there is our answer. A lot of calculus and a lot of pre-calculus skills coming into play, all in one problem.